Yeah, thank you, Anna, again. Welcome back, everyone. So maybe in the first session, I should have given a bit of an introduction myself, but basically, I am the author of Winterfell, or at least one of the authors, and Miden VM is something that is built on top of Winterfell, and I'll explain the reason for doing that. But it is part of this Polygon Miden project, which is the ZK rollup, Start-based ZK rollup. And what we want to do is build a general purpose ZK rollup, using Starks as an underlying proving technology, and we're using Winterfell and Miden VM as kind of the building blocks to achieve that. So the things that I would like to cover. See. Yeah. During this talk is just do a quick introduction to ZK VMs and explain, what they are, why do we even care about them, and some design considerations that we think about when we, build this type of VM. So then go through a very simple toy example of what it would take to build a ZK VM in a Stark context, and then give a bit of a very short deep dive on a architecture of Miden VM, and then show how we could code a, let's say, Fibonacci sequence in Miden VM, or how we would prove execution of a Fibonacci sequence in Miden VM. All right, let's jump in. So the way to think about zero-knowledge virtual machine, and this is by no means kind of the only way to do it. I'm sure there are other ways to describe it, but the way, at least I think about this, if we think about this function that I showed at the very beginning of the last session, where we have a function, we have public inputs, we have a witness, and we have the output. In the context of a zero-knowledge virtual machine, this function is actually instruction execution logic of the virtual machine. So basically something that executes instructions. Public inputs, at least in this description definition, could be like a commitment to the program. So it's not the program itself, but it's a commitment to the program. It's a commitment to initial state of the virtual machine, and also a set of public inputs that go into computations. In terms for the witness itself, we can actually provide the program as a witness, so as a secret input. We can also provide the initial state of a machine as a secret input. And we could also have some secret inputs if we needed to, have, let's say, signatures that don't need to be shared as a verifier. And then the output of the VM is the final state, or actually a commitment to the final state of the VM. And to illustrate this kind of in another way, so let's say this is our zero-knowledge virtual machine. We take commitment to the initial state and the program. This is provided as public inputs. We have things provided as a witness, or as kind of private inputs. The program itself, the initial state, the actual initial state, and the secret set of inputs. This get expanded into kind of the actual, this get compared to the commitments that were provided from here. And then the output is the final state commitment, as well as the proof that the program was executed correctly. So the verifier actually, to verify this transition, the execution of this program, really just needs to know the commitment to the program, commitment to initial state, commitment to the final state, and the proof itself. So the verifier in theory doesn't even need to know what the program was, or what the initial state was, or any other secret inputs that went into it. And this opens up a lot of interesting opportunities for kind of some privacy preserving applications. So why do we care about this zero knowledge virtual machines? So one thing, and probably one of the main things, is ease of use. So in the previous session, I described how you would how to use Winterfell, and described how many things that Winterfell takes care of for you, like the low degree extension and constraint evaluation and all of that stuff. But it is still it still requires you to come up with this arithmetization of your problem, and while it is not necessarily you don't need to study cryptography for 5 years to be able to do that. It is still non-trivial and a very steep learning curve. So while Winterfell helps you and doesn't require you to be a cryptographer to use it, it is still far from ideal in my mind from actually a developer without prior context being able to pick it up and use it, because you need to think about these columns, polynomials. There is still a lot to learn. So with the virtual machine, ideally we can avoid all of that. So you don't need to know even anything about ZKPs to do that. You don't need to even understand what arithmetization is. The other, I think, is a very attractive property is, I mean, for the lack of a better word, is reliability, I guess, here. Basically, what this means is that you can design your error only once, and then you can use the same error to generate proofs for any other computation. You don't need to design error multiple times. This helps in a number of ways. This single error could be audited. It does. Many people can look at it, understand it. It could get much more review. In a blockchain context, you only need to write one smart contract that verifies this specific error. While, like, if you went with the other approach, you might have to write multiple smart contracts, one for each error, and things like that. So in this case, it is. It simplifies things from the standpoint of usability and being convinced that what you're doing, what you're using, has been reviewed and is reliable. The other thing is, especially in the start context, a virtual machine is a very attractive way to address this composability problem that I talked about before. If you think about what a virtual machine is, it has a small transition function, or relatively small transition function, that gets repeated millions and potential millions of times. Anytime you kind of execute a cycle in the virtual machine, you're executing the same exact transition function. So it is very suitable for Stark, which is this uniform computation. So basically, you're describing a uniform computation and can be applied, practically indefinite number of times. So in the context of Stark's, virtual machines are especially attractive. And then last thing is that you can use virtual machines to have basically infinite recursive Starks. All you need to do is, like, if you have a virtual machine, which is powerful enough, and any Turing complete virtual machine will be powerful enough to write a code that can verify a Stark proof of its own execution, you basically get infinite recursion with Starks. So it is not the only way to get recursion with Starks, but it is one of the potentially simpler ones. So this is the main reasons why we care about virtual machines. Or especially in the Stark context, I mean, this I kind of listed benefits. There are potential downsides here. For example, you may argue that by hand you might be able to build better error than that specific, tailored to a specific task. And in some cases that could be true. For simple computations, you can probably build error more efficiently because you don't have the overhead of the virtual machine running on top of it. But as soon as you try to get more sophisticated and write complicated programs, writing error by hand becomes extremely challenging, and doing so reliably becomes doubly challenging, making sure that you didn't introduce any bugs and so forth. So I would say for simple things, yes, maybe doing it by hand is an option, but for complicated programs, especially when a lot is at stake, I think a much better approach would be to use a virtual machine that has, has had many people validate and verify its error and things like that. All right, let's talk about design considerations of virtual machines. So now, I don't know why this happened again. Just a second. So the first thing is which type of the machine, and there are many things. Again, I don't mean to make this list exhaustive in any way. I'm sure there's going to be a lot of things kind of missing, but at least I'm trying to highlight the main points. But for example, for machine type, we can have stack machine, which is, for example, what EVM is, or WebAssembly also uses a stack-based design. It could be a register machine, or which most modern CPUs are register machines. So it could be memory machine, which is an interesting way to think about it, because in the context of kind of this ZK virtual machines, memory is fairly cheap, so you can potentially just operate directly on memory, which is not necessarily true in regular CPUs. The other thing is, how do you handle flow control, basically loops and if statements and all of that stuff. And there are also different approaches to this. So Harvard architecture, von Neumann architecture, One of the approaches that I will talk a bit more is this Merkleized abstract syntax tree approach, which is, I think, unique to Miden VM. How do you provide program to the VM? So I described it as providing commitment, but it's not the only way to do it. So you can provide the hash, for example, which is a commitment, or you can provide a program in public memory, which is then you basically providing program in a clear. You can also do code word commitments, which is a slightly different approach. And all of this, by the way, have their pros and cons and different sets of trade-offs and things like that. Another set of considerations is how do you do function calls? Like, do you allow static or dynamic call targets? Can you have code that can write code within a virtual machine, for example? You can, in terms of memory model, what do you do? Do you have like write once memory? Do you have read-write memory? How do you address that memory? Is it per byte? Is it per field element, or is it something else? And then, what native data types do you want to support within the VM? Can you, at the core level, all of these zero-knowledge virtual machines will have a field element as the core data type. But what can you do on top of that? Can you do regular integers, for example, as the native data type of the VM? Can you use structs, arrays, sets, or whatever else in the VM? And then one of the other things to highlight is which field is your VM going to work over? Is it going to be 64-bit, 128-bit, 256-bit? There are different considerations of why you might want to use one versus the other. For example, the smaller the field, the better performance you'll get. But at the same time, there are trade-offs in terms of like, can you use elliptic curves in small fields, for example, or what kind of, like, if you pick a specific field, what kind of this, what we call the blow-up factor, has to be for proof generation, and which affects the proof generation time, and what kind, how high of a degree of constraints you want to have within your VM and so forth. So there is a lot of kind of like considerations that are related to choosing a field. And again, this is meant to be kind of a high level. This is not meant as a full exhaustive list, but just some set of things that we're thinking about when we're thinking about design of the virtual machine, or zero-knowledge virtual machine. Let's do like a very quick, very simple zero-knowledge virtual machine example and how that translates into constraints and all of that stuff. So let's say we have a toy VM that has only 4 operations. It has this no-op operation, which doesn't do anything. And it's a stack-based VM for simplicity here. You can, do push something onto a stack. You can add values at the top of the stack, or you can multiply them. And we assign these opcodes here, which are conveniently basically just powers of 2. So to describe this VM, we're going to have to build an execution trace. So again, this is not going to be optimized or anything, so I'm just doing it for illustrative purposes. So let's say we have a single column that is going to hold the opcode. We call it C. We're going to have operation flags, basically a set of columns that take on values of 1 if a given operation is executed and 0 if not. So like if all of these are zeros, then we execute no-op. If this one is 1, then we execute a push. If this one is 1, we execute an add. And if this one is 1, we execute a move operation. We're going to have a few columns that will describe our stack. So in our case, the stack is going to be fixed with just, at most depth 4. So as you execute things, you'll push things onto the stack and do operations there, but we have these 4 columns to describe the stack. And then we'll have something called this instruction sponge. As you execute operations, they get absorbed into the sponge, and then at the end of the trace, if you've absorbed a set of instructions, you will get the program that you're expecting that to execute. So basically, this commits or binds kind of opcodes that get executed on the VM to the instruction that to the program that we think we're executing. All right. So with this basic design, let's see how we would perform some operations. So again, these are our columns. So let's say we start in the initial state, which is basically all zeros. Nothing is the VM is in a clean state. We want to execute a push operation. So here, push means we've set this flag to true, which means this the opcode is 1. Set this flag to true. We'll put the actual instruction and the immediate value into this instruction sponge. I kind of put this here as like it will be set to some values, but which values we don't know. It depends on the hash function that you're going to use. So for illustrative purposes, I just use dashes to put in there. But think about this part as containing kind of the rest of the hash of the accumulated program. And again, in reality, it's going to work slightly differently from this, but this is for simplified example. I think this works. And then I'm going to do another push. So again, another push. Now we have, you notice that we pushed 3 onto the stack. Now we have 5 and 3 on the stack. And then we're going to do an add. So notice that the output is now 2. Now this flag is set to true. We've computed an add, and now we have a different. So like our immediate value was set to nothing because add doesn't take an immediate value, and our instruction kind of like that got absorbed into the sponge is 2. All right. So this is kind of like a very simple execution trace. If you think back to the previous session, it's exactly as we were doing with other, like we're recording a state of the computation at a given point in time. And in this case, the state of the computation is the state of the virtual machine. Now, what are the constraints that we want to impose against this execution trace? So let's think about back again as in a setting of we have a current row and the next row in this execution trace, and I'm going to mark the next values with primes. So C and C prime. So C is the current value in the current row in a given column, and C prime is the next value in the same column. So again, this is not going to be comprehensive, just like a few constraints that we would want to impose on this execution trace. So the first one, a constraint that says that we only want to have ones and zeros in this columns, and this constraint basically says that for any I from 0 to 2, we would need to make sure that this expression holds. Like this is the constraint. This is actually 3 separate constraints because we have 3 values for I. But this would hold only if the values in those cells either 1 or 0. It would not hold for any other value. The next constraint we want to do is that we want to make sure that whatever is in this F columns is equal to whatever is in the C column. So it's fairly simple. It's because we've chosen this powers of 2. C minus this expression must always be 0, and this expression is just value from here, plus value from here times 2, plus value from here times 4. The next constraint that we might want to impose is that only one value is set at a time. So we don't want to have a situation where, for the flag, I mean, where we have multiple flags set to 1, because in this model, a very simplistic model, we have a flag per operation. And this constraint basically specifies that. It's a bit complicated of formula, but basically if I didn't make a mistake, and if you run the numbers, you'll see that it's impossible to have more than one value set to 1 here. And then one other constraint, and again, not exhaustive, there's many more constraints that we care about, but one other constraint to illustrate how we will execute the creations is that, again, it looks more complicated, but actually there are different components to it. So what this says is the next value in this cell should be equal, to whatever was previously computed based on whatever the flags are set. So, for example, if S0 prime, minus if we are executing push operation, it would be F0 prime times H1. So H1 was the immediate value that we've put in there. This would evaluate to 0. If the transition was correct and we are doing a push. If we're doing an add operation, then this flag would be set to 1, and then this would evaluate potentially to a non-zero value. So this would have to hold true, S0 plus S1. So these two together should equal, summed up together should equal to this. And same for multiplication and for no-op. So basically, this describes a transition function for different operations, and we kind of just combine them together because we have these flags that are mutually exclusive. This is not the only way to do it, but this is fairly straightforward. And again, there's a bunch of other constraints that I'm not like. There are constraints on the rest of the stack. There are constraints on how you compute operation sponge and instruction sponge and all of that. So this is meant to be kind of like a very high level overview of how you would build a virtual machine. But it is taking this and building a full-blown virtual machine is more complicated from a GX point of view, but conceptually it's not super complicated. There is one thing that we didn't mention here is like how do you use build random access memory, and that requires another kind of set of tricks which have to do with permutation arguments, but these are not yet supported in Winterfell, by the way, something we will need to support to build a more robust virtual machines, and the next version of Miden VM will require those. All right, so let's talk about Miden VM architecture. So at the high level, going back to those choices that or considerations that I listed earlier, we have a few kind of design choices that we made with Miden VM. Specifically, the next version of Miden VM is going to be in this 64-bit field. It's very performant field. It has a number of attractive properties. You can modular reductions are cheap. You can kind of emulate 32-bit unsigned integer operations fairly cheaply in this field. So it has a lot of good properties. The current version, the one that you will see on GitHub right now in the main branch, is still using a 128-bit field, but the one that is being developed in the next branch for Miden VM is already been switched to the 64-bit field. We're using for machine type where we decided to go with a stack machine. There are again a number of different considerations why you might want to choose a different architecture, but for our purposes, at least kind of initial thinking is that stack machine will provide kind of best trade-off between performance and simplicity. We'll see if it turns out to be a correct assumption, because there are definitely other approaches to doing this. Flow control is accomplished using this mask-based execution, and I'll cover this in a bit more detail in the next slide. But this is something that is fairly unique to Miden VM. Most other VMs that I'm aware of are either using a Harvard or Von Neumann architecture to do flow control. Program inputs, and this is related to this mask-based kind of representation of programs, is basically a root of the program kind of Merkleized abstract syntax tree, and again I'll cover it shortly. And this also kind of flows into how to do function calls. So in our case, well, in usual architectures, you do function calls by start executing instructions from a new place in memory or something like that. Basically, you move the instruction pointer to the beginning of the code that describes the function. In our case, functions are hash addressable, so there is a hash of the function that you invoke, and then that gets executed. And that also requires that all function calls, call targets, are known at the static time, because you can only call something that you know hash of. You can't call some function for which you don't know what the code will do. This is an attractive property in my mind in the blockchain context, where you want to have as much kind of deterministic behavior and limited dynamic behavior as much as possible to avoid bugs and things like that. For Miden VM, the memory model is read-write memory, so you can both read and write from memory, and it is word addressable, meaning you can a word in our context is a set of 4 field elements, so you read and write 4 field elements at a time. Or you can, if you interpret those field elements as 32-bit integers, it could be you basically write 4 32-bit integers in a single operation. And there are reasons for why we chose this. I think, first of all, choosing read-write versus write once memory makes sense, because it simplifies programming model, and more addressable memory, in the context that we care about, I think, or the use cases at least that I foresee the VM being used for. I think frequently we need to write in batches, and that actually makes performance, improves the performance of the VM. And then native data types, as I mentioned, we have field elements, but we also, at this point in time, also have regular 32-bit unsigned integers, which you can use, and we will kind of probably, down the road add some additional data types. But at this point in time, it is field elements and 32-bit unsigned integers is the core data types, other core data types of the VM. All right. So at the very, I know this is a complicated chart, and I'm not going to go into full detail of this, but this kind of describes the architecture of this next version of the VM that is being developed right now. the trace itself is, I showed in the toy example we had just maybe like 10 columns or so. The trace for the VM itself is probably going to be closer to like somewhere 80, 90, maybe 100 columns, depending on what optimization we want to do and what functionality we want to support. And there are different parts of the VM. So there is like just 2 system columns, for example, that keep track of like a system clock and some memory pointers. And then there is the decoders, like set of trays that is allocated to decoding instructions and computing this, program, absorbing instructions into the sponge and basically computing this hash of the program as we execute this. There is a set of 19 columns that is used to represent the stack, and we actually can represent stack of unlimited depth using this 19 columns and things like that. So there is like a set of columns that are dedicated to doing efficient 16-bit range checks, because those checks are used in many places in the VM. And then there is a bunch of other kind of segments that are used, what we call coprocessors, where we offload some hashing operations to coprocessor, we offload bitwise operations to coprocessors. Actually, all the random access memory is being managed here and so forth, and we might be adding additional coprocessors to this as we need, as needed if we need to add additional functionality to the VM. The other thing I wanted to mention is that I didn't really address it. I call this virtual tables, but this is basically a permutation argument that allow us to use like this kind of things that I used in Plonk as well for linking different parts of the trace together. So these techniques actually improve composability quite a bit. So if you have access to these permutation arguments, some of the pains of doing composable error goes away. Not all of the pains, but some of the pains do go away. And in our case, we will be using them to kind of like, we have this independent columns. We need to link them together in different ways. And this is what these virtual tables are going to be used for. All right. So let me talk a little bit more about this mask-based execution and what I mean by this. So traditionally, like we think of programs as just sequence of instructions, and then you have an instruction pointer that jumps into a given point in the program and then starts executing from there. And in our case, we approach it differently. So in our case, we think of a program as an abstract syntax tree, and executing a program is basically traversing a path through that tree. So let's say there is some program that looks like this, right? So we have some instructions that get executed. So this is a linear sequence of instructions, and you have an if else statement. In this case, like if true means that if the value on top of the stack is true, then you execute this branch. If the value on top of the stack is false, you execute this branch. And then inside we have some sequence of instructions again, and then you have some loop in there. So this will basically execute while the top value on the stack is true. And then you execute this loop, and then execute this instructions, and then you execute this F1 through Fn instructions. The way this gets translated is, and I'm not going to go into super deep detail on this, but this is kind of an abstract syntax representation of this program, where we have what we call different nodes, or we call them program blocks in a tree. So, for example, a join block is something that means that you execute the left side and then the right side. But a split block, it means you only execute either one of the branches, depending on what the condition on top of the stack is. And then a loop block, it just executes whatever is inside of it until the top of the stack becomes false. So this program can be represented as this abstract syntax Merkle tree, abstract syntax tree. But we also make it a Merkle tree, so you actually can hash each of these blocks, and in the end, the entire program can be represented by a single hash that is the root of the program. And then as you execute it, like as I mentioned, the decoder, you will notice that here a fairly large part of the trace is devoted to the decoder. It actually builds this abstract syntax tree as the program gets executed. For example, if it starts at the top and figures out that, well, this is a join block, so I need to start executing the left branch. So this is another join block, so I need to start executing this. So it executes the A0 through AI instructions, and then it sees that this is a split block. Starts executing the split block, but then it realizes that it needs to first execute, check the condition on the top of the stack. So if condition is let's say true, then it will execute just these instructions and then go back up the tree. But if the condition is false, it will start executing this subtree and so forth. So this is a very, I should say, unusual mode of executing things in the VM, and there are a couple of reasons why we decided to use this. One of the reasons, as I mentioned, that you get for free this static function call. So like if you have a function call somewhere, you have to provide a hash of that function, and you know exactly which sequence of instructions you're going to be executing as part of that function. So there is no kind of undefined behavior in that context where you don't have self-modifying code. You don't have dynamically kind of like chosen call targets and things like that. That simplifies formal analysis and like verifying that the programs are correct and all of that stuff. The other approach in this context is that it's easier to achieve kind of privacy, especially code privacy, in the context of blockchains. For example, if you think about like a contract as a commitment to a program, first of all, you only have to reveal the path that was taken during the execution if you want to reveal something. So like if we build up this hash as we execute the program, but if this branch was never executed, the hash of this branch is provided non-deterministically. So you don't actually need to reveal what happens in this branch if you want to execute only this branch. The other benefits that you get is that you can take this, it's very easy to compose this with other programs and like hide some aspects. So like, for example, if I wanted to have some preconditions and postconditions to this program, I could like build another tree on top of this. And I would say, I'm going to hide this program entirely. I'm going to reveal what the preconditions were and what postconditions were, programs that executed before and after. But I will not provide the actual code of the program. And the verifier, whoever needs to verify execution of this program, can still say, well, yes, I know a program with this hash was executed between these two programs, but I don't know what the actual program in between was. And this could be useful. For example, think about a smart contract where you want to ensure some invariance. You want to make sure that no new coins have been created. So you would count the number of coins in the contract before, and then count them after, and you will compare that before is equal to after. But how they moved in between is completely hidden from whoever needs to verify that everything was done correctly. All right. A few highlights about Miden VM specifically. So I talked about a little bit about some of this already, but what we want to do is make the VM super developer friendly. That means we don't need to know anything about cryptography or even like finite fields or anything of that sort. So it's a regular stack-based machine. It has 32-bit integers as a base data type that you can use. You don't need to even understand what finite fields are. It has read-write memory. Doesn't have native exception handling yet, but will have a native exception handling. And then we're building kind of an extensive standard library with traditional hash functions that, like Blake 3 and Charter56 will be in there, elliptic curve signature verifications and things like that. So we're working on, and obviously to support like, and I'll get into this in a few seconds, but to support Solidity, for example, we will also have like 256-bit integers and all of that other stuff. We don't foresee people will program a lot using Miden assembly specifically, or like the core language of the VM, but we do want to provide multi-language support. So our goal is to have Solidity as kind of the first class language in the VM, but we also want to make sure that other languages can work in the VM as well. A few of the interesting ones that I listed here is Move, that was developed by Facebook's Novi. And then Sway is something that Fuel Labs is working on. So those are pretty interesting languages, and we hope we'll be able to support them as well. Our kind of philosophy on this is that we want people to code in whichever languages that they're comfortable with, and want to make sure that they get compiled efficiently into Miden VM. As I mentioned, we have this very safety-centric design kind of philosophy where we don't want to have, we want to be Turing complete, but at the same time, not the expense of some safety. So the VM is going to be Turing complete, but it's not going to allow some of the things that are, in my mind, are fairly dangerous to do, especially in the blockchain world, where you don't want to have dynamic call targets, for example. You don't want a code that can write self-modifying code and things like that. And all operations in the VM are safe by default. And then, as I mentioned, because of this mask-based approach to program execution, I think there is a fairly good path that we have to supporting both transaction privacy, but also privacy preserving smart contracts. All right, a little bit more about the actual multi-language support that I mentioned. So as I mentioned, Solidity is something that we want to support as a primary programming language, and the way we will do it is through compilation to Yule, and then we actually already have a separate project that there are people who are building Yule to Miden transpiler and doing an awesome job at that. And then Miden assembly is the native language of the VM, and that's what the VM can execute. And as I mentioned, we do want to support other languages, so the model is that other languages will be compiled to Miden assembly as well. Wanted to share some performance goals that we have for the VM. And again, these ones are more preliminary, so take them with kind of like this aspirational goals. Hopefully we can get there, but maybe it's not going to happen immediately. So we have on the single core 25 kilohertz right now. The current version of Miden VM, the v.1, can do about 10 kilohertz on a single core, but we hope with some of the improvements we can get to 25 kilohertz. And then, as I mentioned, this scales fairly well, and hopefully with like GPU and FPGA acceleration, we can get to some number of megahertz. And this is again cycles per second. And some of the ways to get there, first of all, we're using Winterfell as a backend, which is very performant and up-to-date Spark protocol implementation. We're using this Goldilocks field, and that same field that is being used by Polygon Zero at this point in time, which is very fast modular, has very fast modular reductions, and you can has quite a few other attractive properties. And also we will be using this randomized error with preprocessing to like do this, for example, range checks efficiently and 32-bit operations and so forth. So I talked a lot about where we want to get, but here's like where we are now. So V01 is available on GitHub now. It's fully working. The proof generation, all of that is working. It has basic stack manipulation, arithmetic operations, and control flow implemented. V02 is very actively being worked on and should be available maybe in the next 5-6 weeks, maybe some plus minus a week or two. And this will have random access memory, will have native support for 32-bit integers, will have procedures, which is kind of like functions. And then we plan to kind of keep working on it for add storage and modules. Like modules would be kind of like smart contracts, function calls, which is basically cross-contract calls, and then add more cryptographic primitives that are useful in a blockchain context, and then finally, get to a point where you can take Solidity and compile it into Miden VM. Hopefully, sooner than this, but at the very least by that time. I'll skip this part. Let's do a very quick Fibonacci example. We didn't get to do like the actual Fibonacci example of how you write error for Fibonacci in the last session because we ran out of time a little bit. But just to show how to do this in Miden VM. So let's say we wanted to compute the millionth term of a Fibonacci sequence. In Miden assembly, this would look something like this. There isn't really, it's basically like a 10-line program that allows you to do this. You don't need to understand anything about polynomials or air or finite fields. You just can write a typical program that uses like push and swap operations. And this is the program that you can write in Miden VM even right now. Obviously you do need to understand Miden assembly, but hopefully this is a much less of a steep learning curve as compared to like figuring out what air is and how to write algebraic formulas for describing a given computation. And even now, like if you wanted to, this is like a U representation that can get compiled into Miden assembly code, so that you could do this using U as well. U is an intermediate representation, so you probably wouldn't want to write it just like that, but in theory, like if you wrote that in Solidity, it would get compiled to something like this in Yule, and then in Yule you would be able to, this Yule would actually compile into something similar to this assembly code here. All right, I think that covers the content that I've had. I probably went fairly quickly through this. So let me see if there are any questions. Right. Question from Willie: Is there a read-write? Is the read-write memory a problem for the parallelism of Miden VM? Doesn't really come as a problem for parallelism. I don't think. I mean, execution within the VM itself is always single-threaded. There is no kind of multi-threaded execution within the VM. The proof generation is multi-threaded, so you can generate proof in parallel, but the VM itself executes operations sequentially. Now, if we had to work with, let's say, if we wanted to have like multiple transactions as an example and verify them concurrently, that really depends on like the architecture of the underlying, like ledger, for example. Can you do parallel execution of transactions in a given context? And if you can, then maybe we can do parallel execution of those within the VM as well. For example, and in that case, actually, what would make more sense is like recursive approach, where you would verify independent transactions recursively and then aggregate them into a single proof. But you may still kind of like a single transaction will still be executed sequentially. Next question: how much cryptography one needs to know in order to work with Starks? So depends on what you mean by work with Starks. So for example, if you use Miden VM, you don't need to know any cryptography. If you use, or at least you need to understand what the hash function is, but probably you don't need to be very deeply knowledgeable about it. If you use Winterfell, there is a bit more cryptography than you need to understand. It's not cryptography per se, because really what you need to understand is the tarifitization concept. But if you wanted to build let's say, a Stark protocol from scratch, then yes, you need to understand quite a bit of cryptography. And I mean, it's not necessarily cryptography again per se, because there's the hash function being used, but you do need to understand the protocol and all the security trade-offs and all of that stuff, and that is fairly complicated. There's a question: is Miden simply Polygon's implementation of Winterfell, or should we consider it to be the next generation of Winterfell? No to both. Miden VM uses Winterfell as a dependency, as a prover. So Miden, you can think about this as the VM itself has a set of error that is described, kind of describes the execution of the VM, and then we use Winterfell as the proving system that proves that this error was, to generate proofs using this error. So you can think about like we built VDF on top of Winterfell. Miden VM is kind of another thing that you can build on top of Winterfell, but you could. It is not replacing Winterfell, and it is also kind of not next generation. You still need both. It's kind of like a separation. One is concerned about the actual VM and the logic of the VM execution and how you describe it in there. The other one is concerned of how do you take error and generate Stark proofs given the error description. Let's see. Will this particular example be available? This part, I'm assuming it is. We're talking about what I have on the screen right now. There are a bunch of examples in the current Miden repo. I don't think this specific example is there, but there is a code for Fibonacci sequence, which I think is fairly close to this one. There is a code for some other things in there as well. And if you want to look at the new version of Miden VM that is being worked in the new branch or next branch, there are actually code. There is like a standard library of functions already there, which has as simple things as like how do you do a 64-bit multiplication or addition to something as complicated as how do you do like a Blake3 hash function, which is 1,000 lines of assembly code, for example. Let's see.
I don't know if you've reached the end of the questions. We're a little bit over time, actually, so we might need to wrap up. We have to announce the puzzles, and I know that some people are just arriving ready for this too, so yeah.
I'm happy to take some questions at a different time, or like I think there's Discord and I can answer those maybe there at some point.
Exactly. Actually, yeah, if folks aren't already in the Discord channel, there's a workshop sort of sub-thread talk more about all of this stuff. And we'll be posting videos there as well. So, yeah.
Yeah.
Bobbin,
yeah. Sorry if I didn't get
Oh.
to answer some questions, but hopefully I can do it in a different medium.
Very cool. Thanks so much, Bobbin, for the talk on Miden VM.
Yeah, definitely. It was my pleasure. And if you guys are interested, like we are looking for contributors. So if you are passionate about zero knowledge stuff and virtual machines and things like that, drop me a line.
Nice.